Hi folks, today we're going to talk a little bit about hydrogen bonding and specifically how to detect species that are hydrogen bonding and species which are hydrogen bond donors and acceptors, as well as talk a little bit about what hydrogen bonding is. So we'll kind of start there. Most people know hydrogen bonding essentially through water. Water is the classic hydrogen bonding species and it is unique in a number of ways. One of those is that oxygen, which is a quite electronegative element, uh, is pulling hydrogen electrons out of the covalent bonds in a polarized fashion towards itself. So in this case, the hydrogens are slightly positive because they are less electronegative, and the oxygen is more electronegative, and so it's pulling out the electrons through the covalent bond, so there's an unequal sharing. The hydrogen is getting fewer of those two electrons during its time sharing them, and the oxygen's sharing them more, keeping electrons more for itself. The same thing happens on this bond. This hydrogen becomes polarized positive because of the electronegative covalent bond that it has, the polar covalent bond. And so overall, this water is a polar molecule through the additive vectors here that we see. It's really polar towards the oxygen between the hydrogens. And so these dipoles here are important. It makes water have a lot of electron density on the oxygen and very little electron density on the hydrogen. And so we have a semi-charged system here. It's not formally ionic, but it does have a polarity on the bonds, which allow it to do unique things, such as hydrogen bonding. Now, two water molecules can interact through hydrogen bonding. And for example, we could have a water in this mode interacting with the water here, and they would be hydrogen bonding through the lone pair on one oxygen and the hydrogen on the other. And remember that it kind of is a semi-ionic system where we have a quasi-electrostatic attraction here between the negative and the positive, but we also have a semi-covalent bond here. Essentially, you can imagine that this oxygen is kind of attacking that hydrogen like in organic chemistry, but this oxygen can't win versus that oxygen, and so it's essentially a weakened bond, but it's not fully covalent. So these guys can easily escape their hydrogen bonds and find a new hydrogen bond donor. Now, hydrogen bonds are some of the strongest non-covalent bonds that are around, strongest intermolecular forces. And so they're extremely important in solvent properties like boiling points and melting points and all that kind of thing. For example, water has an abnormally high melting point and boiling point for a small molecule like H2O versus something like H2S, which is its downstairs neighbor on the periodic table. Hydrogen sulfide is a gas, the smell of rotten eggs. Water, of course, it has a vapor pressure, but it also is largely liquid instead of gas. And so because oxygen has these properties of hydrogen bonding, it can stay a liquid because it's more attracted to its other neighbors in the solution versus sulfur, which cannot do hydrogen bonding, even though it looks almost identical. It just is not polar enough to be able to hydrogen bond. And so we have a couple things we need to talk about here. This one, in this mode, this water is acting as a donor, and this water is acting as a hydrogen bond acceptor. And when we're talking about hydrogen bonding, the hydrogen is what we're donating. We're donating the hydrogen to the bond, and this one is accepting the bond for the hydrogen through its use of a lone pair. So there's a couple rules we need to talk about. So if you want a hydrogen bond, you need a couple of things that go right for you. You need to first have a hydrogen to donate. So if you're a hydrogen bond donor, you'll have a hydrogen, but it can't be any hydrogen again. It needs to be attached to an electronegative element. The three most electronegative elements on the periodic table are oxygen, nitrogen, and fluorine. So you have to be at least one of those. Now if you look at the periodic table here, nitrogen, oxygen, and fluorine are up here at the top right corner of the non-covalence of the P block. So only those three, the most electronegative being fluorine with an electronegativity of 4, a Pauling electronegativity, is the one that can do this the best, and then oxygen is slightly less electronegative and nitrogen slightly less still. By the time you get to carbon, it's not polar anymore enough to do hydrogen bonding. Likewise, electronegativity decreases down a group, and so chlorine isn't electronegative enough to hydrogen bond, and neither is sulfur, as we just spoke about. So only these three really can be hydrogen bond donors. Now in biochemistry, we really don't ever see fluorine in a way that it's actually bounded to a hydrogen. Because it's a halogen, it can only have one bond, and usually if we see a fluorine anywhere, it's bound to a carbon. So really the ones we care about in biochemistry are hydroxyl groups OH or HN. So now there's other ways we can see these, but those are easy. Donors are pretty simple. If it's an O with an H on it or an N with an H on it, it's going to be able to hydrogen bond as a donor. Now, finding acceptors is a little bit harder. Acceptors can be either any one of those three, of course, oxygen, nitrogen, or fluorine, but they have to have a lone pair. And there's a lot more exceptions to the rule for acceptors than there is for donors. So a fluorine can always be an acceptor if it has a lone pair. If it has a localized lone pair, that is. So these lone pairs must be localized. And it doesn't matter what kind of localized, they need it. Lone pair. And it has to be localized. Now, that implies that a delocalized lone pair is not going to be sufficient to do hydrogen bonding. So anytime we do one of these, we're going to need a hydrogen bond donor and an acceptor. And so we need to have a mix and match of these two. So what we're going to need to do here is find ways that we can have them localized. Now, an obvious one would be like an OH group. OH groups are always going to be a hydrogen bond acceptor on the oxygen, and it's always going to be a donor through their hydrogen. Always the case. I don't think there's ever a situation where you're not going to be an acceptor. Now, you can have a situation where you're going to be somewhat confused about this when it comes to nitrogen. Nitrogen only has one lone pair. Nitrogen can be a donor, of course, through its hydrogens, but whether it can be an acceptor or not depends kind of on the neighbors. Right now, if we just had a carbon backbone, this lone pair would be a total acceptor, right? Because it's a localized lone pair. Now, if we were to put a double bond here and make this into a allylic lone pair, allylic meaning the next bond next to a double bond, oftentimes allylic lone pairs are pulled into a resonance system where lone pairs are delocalized into a larger resonance system. So for example, with this allylic lone pair, we would now have a delocalized lone pair, and this would no longer be an acceptor. This amino group would now be a only donor because this lone pair is delocalized. Okay, so it's only a donor, not an acceptor. All right, so let's think about another case where we could have something like this. Here's a nitrogen with a lone pair. Should be a donor. Okay, here's a situation where we have a nitrogen. This would be like an internal imine. We have an allylic lone pair. And again, I kind of mentioned that allylic lone pairs tend to be delocalized. Now, if the nitrogen already contains a double bond, if this is essentially like a vinylic nitrogen, I don't know if that's the correct term, but if it's already attached to a double bond, that trumps this allylic lone pair thing. That means that this is a localized lone pair. And if you remember what the hybridizations of these atoms are, we have two bonds and an electron lone pair. That would be an sp2 group, and that would mean that this is held out at an angle away from the pi system, and therefore it's a localized lone pair, and this could be an acceptor. So to summarize, it's easy to be a hydrogen bond donor. If you are an oxygen or nitrogen attached to a hydrogen, you can always be a donor. It's really easy to figure that out. Now, if you have a lone pair, usually you can be a lone pair unless it's an allylic system. Now, if we look at oxygen, here would be an allylic hydroxyl group. It's one bond away from a double bond. That means that one of these lone pairs is delocalized. The other one is localized. And remember that all we need to be a hydrogen bond acceptor is to have one localized lone pair. That means that this oxygen atom is an acceptor. And it's also a donor through its hydrogen. This is a unique thing about oxygen because oxygen has two lone pairs. If you have at least one lone pair, you could be a donor. If that lone pair is delocalized because of an allylic double bond, or allylic position next to a double bond, you could theoretically become a delocalized and lose your acceptor abilities, but oxygen has two and has one to spare. And so oxygens typically are always going to be an acceptor. It's pretty easy to look at those and kind of figure that out. Nitrogens, though, are the exception to that rule. So because nitrogens only have one to spare, if they are allylic, they are delocalized, and this would only be a donor because this is a delocalized lone pair. The only exception to that would be if we have already a double bond attached to that nitrogen. In this case, since we already have a double bond, there's already a delocalized lone pair. It's in this this system, this conjugated system, and so this one is a localized pair, and so therefore this is an acceptor. So hopefully that clears a few things up. There's a few ins and outs, but you can kind of summarize that oxygens are pretty much always acceptors. Nitrogens are sometimes acceptors and sometimes not, depending on what their neighbors are doing. Okay. So let's look at a couple of molecules and see if we can figure out what kind of acceptors and donors they have. So here we go. This is histidine. Histidine is a amino acid, and it has a lot of hydrogen bond donors and acceptors, like many amino acids do. So for example, here's our carboxy group of the amino acid. I'm going to draw in all of our lone pairs, just so we can kind of see what's going on here. We also have one down on this ring nitrogen. So oxygen here, we have a lone pair. We are attached to a double bond. That means both of these lone pairs are localized. That means that this is an acceptor. So remember that double bond rule. If you're already on a double bond, you're an acceptor, and you have a lone pair, you're automatically an acceptor. Here, this oxygen has a delocalized lone pair, but this one is localized because we had one to spare. So this one's delocalized, but this one is still localized, and so this is an acceptor. And we also have a donor. So this oxygen can accept and donate hydrogen bonds. This one can only accept them. This nitrogen has a lone pair. It is not allylic or attached to a double bond, and so this is a localized lone pair. It is an acceptor, and it is a donor. So we have a lot of hydrogen bonding going on in the backbone of amino acids. That can change, of course, when we make a polypeptide, but for individual amino acids, we have a very polar backbone. The carboxyl and the amino groups on the backbone are certainly hydrophilic. Now, when we go into the side chains, we have a few things we need to look at. This nitrogen has a lone pair, but it's allylic. Do you see how this lone pair is next to a double bond? That means we can push to make a double bond, and this aromatic ring can essentially have all 6 electrons involved. That means that this is only a donor. And remember that it's a donor because it has a hydrogen attached to it. Now to finish up, this is not an acceptor. This one, this lone pair, we are allylic, and so you might think that this one can be delocalized. But because we already have a delocalized lone pair through this double bond attached, this one is a localized lone pair, and so this is an acceptor. So remember that rule. If you already have that double bond and a lone pair, you are going to be an acceptor, just like this oxygen was. Okay, so that's a full description of hydrogen bond donors and acceptors in histidine. Let's try a different one. Here we have a friend of mine. I believe this is theobromine. It's a chocolate molecule. We have a number of groups here. So let's go ahead and label up all of our lone pairs. Nitrogens always are going to have 3 bonds in a lone pair at most normal pHs. And oxygens will have 1 or 2, depending on what's going on. Mostly 2, if they're neutral. So now we have a series of electrons. Now this carbonyl is the same situation as we just saw. We have 2 localized lone pairs because it's on a double bond already, and so that's going to be an acceptor. This nitrogen has a lone pair, but it's allylic, and so this is neither an acceptor nor a donor. Because remember, this lone pair is delocalized into the system here. This one also, we have a lone pair, but it's allylic, and it's allylic both directions. So this is only a donor, not an acceptor, because this is delocalized. Acceptor here, for the same reason as our other carbonyl was an acceptor. Now we're over here. We got a lone pair on this nitrogen, but it's allylic, both directions. This is neither a donor or an acceptor. Even though it has a lone pair, it is not localized, and so it cannot be used in hydrogen bonding. And then we have, finally, this lone pair. It is allylic, it's next to a double bond, but this nitrogen already contains a double bond, and so this is a acceptor. We have that trigonal planar thing going on here, so this is out on one point of the triangle, the sp2 triangle. So it's localized as a lone pair, and so it can be an acceptor. Okay, here's a Frankenstein molecule I made up. We'll see if we can follow this one. This has pretty much anything you'd ever be asked. Okay, so here we go. We have a guanidino group over here. That's something you might see on an amino acid such as arginine or in a guanine or something like that. We have a heterocycle here, and we got a series of different groups. I'm going to go ahead and throw out all of my lone pairs. That's not very clear. Let's clean that up. This nitrogen 2, heterocycle. Sulfur has 2 lone pairs. Oxygen's got 2 lone pairs as a hydroxyl and as a carbonyl, and we have 1 here. So we're going to go through this thing left to right. Sulfur. Sulfur, can it be a hydrogen bond donor or acceptor? It has a hydrogen on it, but remember, it's not electronegative enough to do it. So this thiol is not a hydrogen bonding species, even though it is somewhat polar. It's not polar enough to do hydrogen bonding. Now here, this hydroxyl group, we have 1 lone pair that's delocalized into the allylic position, but this one is a localized lone pair, so we are an acceptor. And then we also have a hydrogen to donate. So this oxygen is a donor and an acceptor. This carbonyl oxygen already has a double bond attached, so it's an acceptor. It has no hydrogens to donate, so it can't be a donor. This nitrogen is a localized lone pair, and it is not allylic. It is too far away from this double bond, so it is an acceptor and a donor. So that amino group is far enough away from a double bond that it can do both. Okay, this nitrogen, we have a lone pair. It's already attached to a double bond, even though it's allylic. That trumps it, and so therefore we have a acceptor on this pyridine ring. Okay. Down here on the guanidino group, allylic lone pair, but it has a double bond, so that's an acceptor. Then we have a couple of lone pairs over here. Those are only allylic, they don't have any double bonds, and so those cannot be acceptors, but they certainly are donors. So, if you can practice these on any kind of system, you would be able to know where all your donors and acceptors are and know how to predict whether something is hydrogen bonding or not. Hope that helps. Thanks a lot, guys. See you later.